like to thank the organizer for the invitation to participate in this wonderful conference. It's my honor to give a talk here. So today I will talk about spherical QC manifold and how to construct some conformal invariants, and convex co-convex subgroup. Will give some examples and connect to the uniformization problem I will mention later. So let's begin with the definition of quaternion contact manifold. It's a generalization of contact manifold. So it's usually dimension 4n plus 3. First, we have a codimension 3 distribution. H is defined as a kernel of 3 1/4. So it's different from contact manifold. On contact case, we have only 1/4. And we have a Carnot-Cassiodori matrix on G on H. And we have some quaternion structures. We have 3 almost compact structure, I1, I2, I3. So this is not a new, this structure needn't to be integral. So they only satisfy I squared equal to minus identity mapping over H. And also they satisfy the quaternion relations that are last line. They satisfy the first, the I is isometric. The first is isometric, and some compatible conditions. GISXY equal d theta s. And for xy is horizontal vector field. So the choice of one form capital theta is not unique. You can rotate these 3 one forms. This notion is introduced by French mathematician Picard in year 2000 from some other motivations. He also proved there exists a canonical connection that will be useful for studying such manifold. When in the high dimensional case, for the 7-dimensional case is proved by Dutchman in 2006. So this manifold is the quaternion version of CR manifold in complex variables. And we call Picard connection is the generalization of Tanaka-Webster connection. So let's see, the model case is the quaternion Heisenberg groups. So here, here is YT. Y is in HM, and the T is imaginary quaternion inverse. And the multiplication is PRT plus T prime plus 2 imaginary part Y bar is a conjugate and Y prime. This is the quaternion Heisenberg group. So we need the multiplication in terms of real variables. So Y is in R4N and the T is in I3. We can write the multiplication in terms of the quadratic polynomials, quadratic forms. So we have 3 matrix B1, B2, B3. And this in terms of but and the B1, B2, B3 also satisfy the commutating relation of quaternions. Then we can write down left invariant vector fields just by definition. And our horizontal subspace is spanned by these 4 n vector fields. And R3 valued contact form is just similar to the complex case, but here we use quaternion numbers. And CC metric is just y alpha, y beta is orthonormal. And the quaternion structure is the 3 transformations acting on the HVM. You just use the matrix I mentioned before. And also we have subroutine, we use the subroutine. So we see, so the manifold MGQ is QC conformal to MG if G is the G multiplied by some positive factors. So the general definition. A mapping is called conformal QC mapping if the pullback of G is the G times some positive functions and the quaternion structure is preserved. So if F and F inverse both conformal QC mapping, we call conformal QC diffeomorphisms. And the spherical QC manifold is the simply QC manifold. It's a locally conformally QC equivalent means diffeomorphic to an open set of the quaternion Heisenberg groups with the standard structure, but it's right as U. G0 is the standard matrix on the quaternion Heisenberg groups, and we can have some multiples. So where this definition from? Is from the high dimensional generalization of Riemann surfaces. One is the locally conformally flat manifold. Is a Riemannian manifold locally conformally equivalent to the Euclidean space. And in the several complex variable case, is called the spherical CR manifold. Is a pseudo-Hermitian manifold locally conformally equivalent to the Heisenberg group. So this is the quaternion version. And there is a topological description of a conformal class. A conformal class of locally conformally flat manifold can be described as a manifold whose coordinate charts are given by open set of the Euclidean space, and the transition mappings are provided by elements of SO, which is a Mobius transformation, and the spherical CR case is the SU, the group in SU. And in our case, we will need SP n plus 1, 1 as the automorphisms of the quaternion Heisenberg groups. So it consists dilations, usual dilations, and the left translations, and the rotations. Because quaternion number is not commutative, so we choose the matrix acting from the right. And the SPN is the quaternion orthogonal matrix, the group. And we also have inversion, similar to the Euclidean and the Heisenberg case. And one special actions does not appear in the Euclidean and the complex case is because we can left action unit quaternion numbers, and this conjugate in the second step. This one is special. So a conformal class of spherical QC manifolds is a manifold whose coordinates are given by open set of the Quaternion-Heisenberg group, and the transition matrix are provided by elements of ST, n plus 1 well. So can we give some examples of spherical QC manifolds? The first one is called a connected sub. The second is given by a discrete subgroup. So what's connected sub? So I have a picture here. We have two spherical manifolds, and two neighborhood is as two neighborhood is UI. UI is identified to the ball of the Quaternion-Heisenberg groups. We remove some closed balls here, remove here, and we have two manifold, and we identify these two parts. That means we identify to these three. So we should have in this form, this boundary is the inner boundary to the outer boundary. So we identify this one and this one. The problem is we should identify the inner boundary to the outer boundary. So we glue U1 T1 to U sub 2 T1. These two annulus. By the following method. So this annulus, we take a refraction, it becomes this one. So the radius here is t, and after refraction it becomes t 1 over t, and then we take a dilation to the original radius. So first we can rotation this annulus, and then this also some rotations, and take an inversion. So this inner boundary becomes outer boundary, and then we contract to the original ones. So in this way we can glue these two annulus to get a new, more complicated spherical QC manifold. So the problems as in the serial and in the serial Riemannian surfaces, we hope to construct some conformal invariants independent of the sub-Riemannian metric you choose. Second is classification of such conformal classes and the uniformation problems, and even some modular space. These are general problems. So the first, how to construct the conformal invariants, we need several operations. So here the volume form, we have three contact forms, theta 1, theta 2, theta 3, take a wedge, and d theta s, wedge 2n times, we get our volume forms. This volume forms is independent of s, and the several operation is the usual one. Laplace u times v equal to dvu is something like a horizontal gradient. It's just a horizontal. It is written in another form here. So this is the usual subproblem. Our operator, we construct the QC Yamabe operator is the subproblem, some coefficients plus the scalar curvatures. So SG is scalar curvatures, and this is some coefficients. GACT in his paper also proved the transformation formula of the scalar curvature. If we take a G tilde is G times e to the power 2h, this make the vector is positive. Then the SG tilde will have some transformation relation. So we can prove the conformal convergence of the QC Yamabe operator. That means LG, the Yamabe operator associated to the matrix G acting on phi F. Phi is the conformal factor. So we have some specific power here just for convenience. Phi F is any functions. LG phi F equal LG tilde F and some conformal factors. This operator is called conformal covariant. The best we can expect is conformal covariant operator because there is no conformal invariant operator. Covariant means we have factor phi here. If this phi disappears, it becomes invariant. And the invariant will give us the invariant of the manifold. So the G, capital G is the green function of the QC Yamabe operator, just means L acting on G equal the delta functions at point C. And if we transform the matrix, the green function changes very nicely in simple way. G tilde equal G, but G cos eta, and this is the conformal factors here. So green function transform in a very simple way. Because L is not invariant, it's just a covariant, and the G tilde also covariant. So where is the invariance here? This is the green function of the it's just a fundamental solution to the Laplacian, because in the Quaternion-Heisenberg group, the scalar curvature is 0. The Yamabe operator just sub-Laplace. So this essentially know from Kaplan, but here we can just check it directly by calculation. So it's the usual green functions. The power is q minus 2. Q is the homogeneous dimensions. This is the norm of the Quaternion-Heisenberg group. So the QC manifold can be divided into 3 classes. It's called scalar positive, scalar negative, and scalar vanishing. It means we can find a conformal G tilde conformal to G, which has either positive, negative, or vanishing scalar curvature everywhere. So it's equivalent to the first eigenvalue of the QC Yamabe operator is positive, negative, or 0, just equivalent. Or the QC Yamabe invariant is positive, negative, 0. This is the conformal properties. So what's quaternion contact Yamabe problem? That means we find a conformal theta prime equal theta times some positive functions such that theta prime has constant Picard scalar curvatures. This is the quaternion contact Yamabe problem. Such U exists if and only if you satisfy the Yamabe equations. The superapplying this is some constant scalar curvatures times U equal lambda U, so Q plus to the power Q plus 2 over Q minus 2. And we have Yamabe invariant. Invariant is this is essentially the horizontal gradient square plus S scalar curvature times U square. And the P norm of U is equal 1 and P is the Sobolev exponent. And take infimum, we get Yamabe invariant. This invariant is the invariant of conformal class. So many years ago, I studied this problem, and the result is Yamabe invariant is less than equal to the Yamabe invariant of the quaternion Heisenberg group. If lambda m is less than lambda h, then the problem can be solved. So in our paper we need this result. So lambda m is less than lambda hn is called subcritical class. And the critical class means lambda m equal to the lambda hn equal to the Yamabe invariant of the group. This is the much difficult case. Some European mathematicians they studied this case for n equal 1. And it involved to determine the extremes of the Sobolev inequalities. It means the P norm of U square less than the horizontal gradient. When this is the Sobolev inequality for some sharp constant, and H this inequality becomes equality if and only if U is the dilation and translation as some no function. I do not write the specific form of this function. This is not. This result is proved by Jellison Lee in 1989 in a very complicated method. Generalized it's actually differential geometry method. Recently, Lieb and Frank in Princeton, they find a new method to prove the extreme for the Sobolev inequality over the Heisenberg group. This method can be generalized to the quaternion Heisenberg group. So now we can construct the green function. We should consider scalar positive QC method. This is because the eigenvalue, in this case, the eigenvalue is positive. So the operator has inverse. So we have green functions in this case. Otherwise, you have some zero eigenvalues complicated. So the green function is essentially the fundamental solution of the group under this metric G0, some conformal factor. This is the singular part. The G minus the singular part is a smooth function. So So in spherical case, the green function is a very simple form. Is the standard, the singular part and the smooth part. We can split. Usually, this part is to the power q minus 2. It's supposed to have some lower order, but not there. So now we can consider this quantity, the green function minus the singular part, and take some power. This will be our conformal invariant. So the result is this quantity square times g is conformal invariant. So the many results in this talk is appeared in this paper. So the problem is A is non-vanished. If A is positive, then this is the invariant matrix. Otherwise, we can see is a matrix is just some tensors. So here we have the problem we call the QC positive mass conjectures. I will do not explain the details. It's just equivalent to in the CR case, equivalent to the positive mass conjecture. It just means that this green function minus singular part is take a limit eta to consider is non-zero. So the positive mass conjecture actually equivalent to this statement. So the conjecture means this quantity is non-vanished, and A squared G becomes a matrix. So the history is like this. The Lee in MIT gave us the statement of the CR positive mass theorem. Is similar to our case, but his proof has a gap. Only 2 years ago, Zheng Qiu in Taiwan and Paul Yang in Princeton, they gave a complete proof of the CR positive mass theorem. And such kind of invariant matrix may remind you that the matrix in the Riemannian surface is the hyperbolic, some hyperbolic invariant matrix. It was generalized to the locally conformally flat manifolds by Haberman and Yost in last section, and is for spherical CR case by me several years ago. Now let's consider the discrete subgroup. Now SPn plus 1, has another simple description. It's just like SOSU. It's the n plus 2 times n plus 2 quaternion matrix, which preserve these hyperemission forms. We have the minus n plus 1 minus and only one positive. Plus is similar to, if you require PQ real, this becomes SO. And PQ becomes complex vectors. It's the SU, the group SU n plus 1, 1. And if you allow PQ's quaternion numbers, quaternion vectors, it becomes SP. SP n plus 1, 1 acts isometrically on the unit ball of the n plus 1 quaternion space when the ball is equivocated with the quaternion hyperbolic matrix. So the unit ball with quaternion hyperbolic magic, this group can be acting on this on the ball isometrically and act conformally on the boundary of the ball. The sphere is the QC standard QC manifold. The sphere with the standard QC metric, this group acts conformally. So actually we have some Liouville type theorem. This theorem is a folk theorem, but it's appeared was proved in last year paper. Every smooth conformal QC transformation between orbit subsets of the sphere. The sphere is the restriction of a global conformal QC. Global one is means the group SP. We also have Carré transformation from the Heisenberg group to the sphere. We need some transformation. The pullback theta 0 is the contact form on the group. Pullback by the Carré transformation becomes the theta s, and some rotations. It is not only a conformal factor. You can rotate it by some unit quaternion. Now, what's convex co-compact subgroup? So let gamma be a discrete subgroup. We consider the orbit that is now we have the quaternion hyperbolic space. We take a cube, and gamma Q is the orbit, means the group acting on Q. G G1 Q, G2 Q. So it is the orbit, and the orbit has a limit set. It's called lambda gamma. So lambda gamma is the limit, called the limit set, is the closure of the orbit intersection with the sphere. So it's a small set in the boundary, called the limit set. And the omega gamma is the sphere minus the limit set. Limit set is the closed set. So omega gamma is the complement to the limit set. And omega gamma over gamma is the gamma is the convex co-compact subgroup. Is equivalent to means that the omega gamma over gamma is a compact spherical QC manifold. There's many equivalent definitions of this kind of group. This is a geometry one. It just means the complement of the limit set modulo gamma is a good manifold. So let me give some examples. Examples called Schottky groups. So you take two DII is the ball in the Heisenberg groups. You have two balls, and is centered, for example, PQ. So, so the group is things like you can map Q to infinity and P to there. This is by translation, and this complete from diffraction, and you take so you just take dilation. This from here, this boundary to here. You take dilation, mapping this boundary to this boundary. So you have an elemental group map this one to this one. So this is a subgroup generated by one element. You identify this one to this one, you get the torus. So it just Hn minus d1. This is d1, d2. And the modular dilation, it becomes torus. So a little bit complicated is this one. This is element. You can remove another pair of two balls of the Heisenberg groups and map this to things like you have two. This is two balls, and you identify the end. It becomes like this one. So you can take. This is exactly the kinetic sum. It's called Schottky groups. Works here also. So there is many such groups. So the uniformization problem is to show scalar positive spherical QC manifold is equal to omega gamma, modulo gamma for some convex, co-convex subgroup. It's just like in the Riemannian case. It has a long history. For the locally conformally flattened Riemannian manifold, it is proved by Luxion and S.T. Yang in 1988, and Chen-Chu and Paul-Yang in the paper I mentioned before, proved for spherical QC CR manifold. We must assume they are scalar positive. The Yamada invariant is positive. Their method works in this case. So the problem is to find how to find this subgroup, the group gamma. Essentially is the fundamental groups of the manifold, the gamma. Now, given a group, we have Poincare critical exponent. That means we take 2 point PQ, then calculate the distance P. That means any P and any Q, and we take a distance. This is gamma Q, and this is the P gamma Q distance. The distance is the quaternion hyperbolic distance on the unit ball, and times S. Take exponential and summation over all elements of the group. If this is infinite, that S is good, and we take infimum. This number is called the Poincare critical exponent. It connects to the convergence of these fields. So it is no delta gamma is independent of the particular choice of the point PQ. It's the same number for different PQ. So there is a measure support on the limit set of this group. It is known for any rank 1 Lie group. The convex co-compact Klein group, Klein means some non-trivial subgroup of rank 1 Lie group. We can find a probability measure supported on the limit set. So it's originally in the Riemannian case, Riemannian surface case by Patterson and Sullivan generalized to the SO, and Collins generalized to the any that one Lie group in 1990. So this probability measure has some conformal. It is called some conformal measure. Its pullback acting by the elemental group is the same measure, but you need to multiply some factor. And this exponent is the Poincare exponent. This is the same, is also the statement of this paper. And small deformations of the inclusion maps gamma isomorphically to a convex co-compact group. So that means such groups, there's many such groups. You can small perturbated the imagine. And the limit set is a fractal. It's not, also by Collins. So this measure is comparable to the delta dimensional Hausdorff measure. That means the dimension of this fractal is delta gamma, is Poincare exponent. So this Hausdorff measure means the BR is a ball on the sphere under the CC distance. First of all, is the Heisenberg group's non-isotropic ball. The mu gamma on this ball divided by R delta gamma is bounded by two constants. So essentially, we know the dimension of the limit set. So this is the CC distance. I think everybody knows this definition. Here. Now we can construct another QC metric of my tiny type. Just this is the green function of the sphere. We integrate with respect to the conformal measure supported on the limit set, and take some specific power. In this way, phi gamma is invariant. Phi gamma is conformal under the action of discrete group. That means this we construct this G gamma is in the complement of the limit set, and the group acting on the gamma very nicely, and we can modulo gamma to get a matrix on the omega gamma modulo gamma. So we can calculate the scalar curvature of this metric to obtain the following theorem. The delta gamma is less than 2n plus 1, greater than 2 plus 1, and equal to plus 1 if and only if the scalar curvature is positive. This means the manifold scalar positive, negative, and vanish. That means the Poincare exponent characterize the manifold, the scalar positivity. Just calculate the scalar curvature. So such problem, the first one is also Lichung and Yang. They only a partial result for locally conformal effect in many manifolds. And Japanese mathematician Nayatani generalized it and proved completely this theorem for locally conformally flat manifolds, and can be generalized to spherical CR manifolds by Nayatani and myself independently. So next we can consider spherical octonial manifolds. In this case, the group is the F4 minus 20 of the exceptional Lie group. And in this case, the one difficulty is we should know how this group acting on the octonial Heisenberg groups. It is a little bit complicated, but we can write down the explicit action. So I will stop here. Thank you.
Any questions, remarks?
Can you give a definition of convex subgroup, not necessarily co-compact?
Sorry.
Convex.
What is a convex subgroup, the definition?
Convex co-compact. So,
Not necessarily co-compact.
examples of
Definition.
Definition.
Explicit definition means the every limited set is larger. This is one definition, larger. Larger limit set. So what's larger limit set? So for any limit set, you have geodesic, and you have a called a tube. In this tube, the distance, so this is an infinite number. In this tube, is strictly limited to this set. This is called larger limit set. If every limit set is larger limit set, this group is called convex co-compact subgroup. In other cases, you mean the limit set is taken in this way, the tangential way. This is excluded.